Welcome back to the next session of the paper presentation. This session is focused on cryptographic constructions, and for this session we have two session chairs, Professor Sanjeeva Prasad and Dr. Nilotpal Chakraborty. During the session, you can post your QA in the chat box of the event platform itself. So over to you, to the session chair. Thank you.
Thank you, Paulami. Welcome to session 8, and we have 3 talks in the session. The first is Exynos, an efficient, verifiable, dynamic, symmetric, searchable encryption scheme with forward and backward privacy. This will be presented by Chiara Marcola. The next talk will be Smooth Zero-Knowledge Hash Functions, which will be presented by Hamid Reza Khoshakhlagh. And the third talk is another use of the 5-card trick, card minimal secure 3-input majority function evaluation, which will be presented by Kodai Toyoda. The speakers will speak for 15 minutes and have 5 minutes for questions and answers. And after the session, they will all break out into Google Meet rooms where you can interact with them and ask them more questions. During the talk, you can always type in your questions into the chat box, and I can read them out. And those who are in the live audience will likewise have an opportunity to ask questions. Thank you. Over to you, to the first speaker.
Thank you. Okay. Hello, everybody. I'm Chiara Marcola from TII, Technology Innovation Institute in Abu Dhabi. And today I speak about an efficient, verifiable, dynamic, symmetric, searchable encryption scheme with forward and backward privacy. This work is joint work with Najwa, Xiaojie, and me. So what we are going to see is an introduction on searchable encryption with the basic notion. After that, our scheme in detail, and then a comparison with the state of the art. So what is a searchable encryption? A searchable encryption scheme allows a client to outsource his data to a cloud. And then the cloud can search inside this data. So what we have to do? First of all, we have to build a database that link each keyword to a document. More precisely, each keyword is associated to a set of index, and each index corresponds to a document that contains the keyword. After that, we have to encrypt its database and send to the server. In the server also we store the encryption of the documents. So now, suppose that I want to search a keyword, W, and I want to search all documents that contain in this keyword. So I send the query to a cloud, the cloud runs the search and give back the encryption of either the encryption of the indexes or the encryption of the documents. Now we have also a dynamic set. In the dynamic set, we can also update or delete some document. So, and this update is in the safe way, so we can do in the encryption way. And so we can modify the encryption database in this way here. Of course, there is always a trade-off between efficiency and security. And if we want an efficient scheme, we have to allow the server to learn something. So for example, the information that the server learns during the setup phase is called size pattern and includes the number of encrypted files containing the keyword. Now, during the search phase, there are other 2 kinds of leakages that is called search and access pattern. The first one permits to the server to learn how many times and when the keyword has been searched, and the access pattern, which file are retrieved. Of course, in the dynamic setting, we have other kind of leakages, but we want to prevent that the server learn any link between the previous search and update document. And this kind of security is called forward privacy. Instead, the backward privacy prevent information leakages from delete data. Also, in this case, we have different kind of leakages that we have to permit. So we have three kinds of backward privacy. The first one is the more safe, relieves the time of matching certain file, the total number of update, and the matching document associated with the keyword. The type 2 reveals also the time of each update. And finally, the type 3 reveals which kind of update is, so if we insert or delete a document. Now, until now, we consider it a server that is honest but curious, but there is also other kind of server that is called malicious server. And this server can send back incorrect or incomplete result. Now, if a scheme is able to detect this kind of behavior, it's called verifiable. Our scheme is the first verifiable dynamic symmetric searchable encryption scheme, which achieves both forward and backward privacy. And in our case, the backward privacy is of type 2. So relieve the time of each update, but not which kind of update is. Now we are going to see in detail our scheme. So our scheme is based on the principle of additive and secret sharing. What does it mean? So we can consider the keyword that is associated with this set of indexes. Each index is obfuscated with a random element. This random element is a secret sharing, and the XOR of this random element is stored to the server side. Then we have another element that is not random, that is needed to reconstruct the secret that is saved to the client side. Okay, so suppose that our keyword W1 is contained into document 1 and 3. Now what we have to do? First of all, each keyword is linked with a secret that in this case is just a string of 1. Then we have to compute 2 secret key that is linking with this keyword. And then we obfuscate the first index. So we choose a random element that is the obfuscated index. We XOR with the secret that is just the string of 1, and we store it in R. After that, we compute the first position with this function that actually is just a hash function that take as input a secret key and R. In this position, to the server side, we store the XOR with the hash function of R and the obfuscate index. After that, we computed the second position with the same function. In this case, the input is just the secret key and the obfuscate index that is different respect here. And in the second position, in the server side, we save the ciphertext that is the encryption of the operation. In this case, is insert because we add the document, and the index that is the index 1 of the first document. After that, we go on with the second index. And what we are going to do, so we do exactly the same. We obfuscate this index with a random element. We update R with XOR with this new obfuscated index. We compute the 2 positions. In the first one, we save the obfuscated index of the third document, XORed with the hash function of the new R. And in the second position, the new ciphertext. To the client side, in this case, we save the link between the keyword and our R, that is the XOR of all the secret sharing. Okay, now suppose that I want to find the documents containing the keyword W1. So the client has to, first of all, find R with in the dictionary, and then compute again the 2 secret key. The second store, and the first one sent to the server with R. With these 2 elements, the server is able to find the first position, In the first position, we have this element that stored with the hash function of R. We are able to find the obfuscate index of the document 3. With this index, so obfuscate index, we do two stuff. First of all, we are able to find the position where we store the ciphertext, so the encryption of the index, and then we start to reconstruct the secret. So we XOR it to R, we cut the last part, and we update R. With this new R, we go on, we do exactly the same operation, and we find the second ciphertext. So first of all, we compute the position where we store the VED1. With this, we XOR with the hash function of R. We find again the obfuscate index, in this case of the first index. We find the ciphertext and we reconstruct the secret. Now the server, because it XOR both of the secret share, find S, that is the string of 1. So it knows that there are just 2 ciphertexts that he have to send back to the client. So send back these 2 ciphertexts, the client with the key is able to decrypt and find the documents. Okay, now we want to update. To update, suppose, for example, that we have the document number 8 that contains the keyword W1. So we want to add it in our database. What we have to do? It's very similar as before. Indeed, we have to find again our R and update it with a new obfuscate index. So we take a random element, XOR in R, and update R. At this point, we do exactly as before. So we compute the 2 positions, Y, so the new XOR between the hash function with the obfuscate index and the encryption, and send to the server. Now the server that have these 2 couples update in position 1 corresponding to the index 8 VIDA, and in position 2 the new ciphertext corresponding to the index 8. Of course, as you can imagine, the deletion is exactly the same. So if we want to delete the document, for example, the document 3, we have to do exactly the same operation. So we have to obfuscate again the index that we want to delete. And the unique thing that we have to change is here. So the operation, instead to put insert, we have to put delete. So in the ciphertext, here we have delete. And then send again to the server the tuple, and the server update the dictionary. Now, the scheme that I present until now is not verifiable, so it's not able to detect if the server is malicious. To modify our scheme is very simple to do it verifiable, because what we have to do, we have to modify just the update and the setup phase, specifically in the encryption. So here in the encryption, we have to add the obfuscate index. So we have the kind of operation, the index, and then we add also the obfuscate index. So when the server gives back the ciphertext, the client is able to reconstruct the secret. And if it's found after all the operation, if it's able to find S, so the string of 1, it knows that the server is not malicious. Okay. Now we are going to see very fast the performance comparison with the other scheme. In particular, some of the scheme. As I already mentioned before, there is always a trade-off between security and efficiency. In this, as you can see, for example, Moneta and Janus, they are, Janus is much more efficient. Indeed, the computation and communication complexity is better than Moneta, but the security here is backward privacy, so it's less secure than the type 1 of Moneta. So now, if we consider just Fides, Mitra, Aura, and our scheme, that are all schemes that achieve forward privacy and backward privacy of type 2, all of these schemes are not verifiable, indeed, because our is the first one that achieve also the verifiability. And as you can see, these schemes are very similar to our computation and communication complexity. The difference here is the query complexity. Indeed, our is constant and not this. Our query complexity is a bit better. Now, if we focus on Sophos and Mitra and our scheme, for example, so Sophos has exactly like us communication and communication and computation complexity, but is not achieved backward privacy and is not verifiable. Actually,
about a minute to go.
Yes, I almost finished. Thanks. Yes. So actually, Bost also had a verifiable scheme in his paper, but the client storage increase. So now, Mitra in this case is very similar to us, but as I already mentioned, the query is big. Indeed, if we are going to see our two picture here, we can see that search time per each matching entry. Sophos suffer a bit the number of documents. Mitra and our scheme is constant, so it's independent to the matching document. And Mitra is a bit better because for each document, it spends 0.3 microseconds to find, our 0.9. But as you can see here, the query generation time in our case is constant, so is independent to the matching document. Instead, Mitra, for example, is linear, so grow respect to the number of documents. Okay, thank you for attention. And here we have some references. Okay.
All right. Thank you, Chiara. Are there any questions?
Yeah. Any questions offline? No questions from the audience. I have only one couple of questions, couple of basic questions. So
Yes.
The first one is that, can you please repeat how you computed R? Probably it was in your slide number 8 or 7.
Yes.
And the second question is that how dependent your scheme is based on the hash function that you used.
Yes. So the hash function that we take is collision functions. Let me check because I wrote. Can I share again the screen or not? It's better to know.
Yes, please. Go ahead.
Okay. Thank you. Because it's more simple to explain in this case.
And he said slide number 8.
Yes, indeed. So let me see if here I write the hash function that we use. Yes, collision resistant hash function with 256 bit. And here, where I compute R, that I guess that is here, the first that I compute R is the XOR between a random element that obfuscated the index and this S that is the secret, that actually is not really a secret because everybody knows that is a string of 1. So when you reconstruct the secret, at the end, you know when you arrive at the end of the chain because you find the string of 1. I hope that I replied to the questions.
Yes. Thank you. Over to you, Dr. Prasad.
Are there any other questions? A very quick question which I had is, if you had an honest server, but you had the malicious observer of it, are there concurrency effects, given that many people could be querying the database at the same time, that could reveal some side channel information about how these queries are related to each other? If I have two related sets of queries, and could I be able to get correlations out of that?
Depends. So we are there is some leakages that are permitted. So there are permits and leakages respect, for example, if I ask a query to the previous queries. But is not permit, for example, if I update a document, the server is not able to know this updated with the previous query that I already asked to the server.
Okay. Thanks very much.
Thank you.
We're ready to move to the second talk, which is smooth zero-knowledge hash functions. And the presenter is Hamid Reza Khoshaklag. I hope I've pronounced the name correctly.
That's correct. Yes.
Go ahead.
So first of all, do you hear me well?
Yes, we hear you well. Could you please share your slides?
Yes. So, okay. Is it shared now?
Yes, go ahead.
Okay, great. So, okay. Hello, everyone. I'm very happy to be here. So today I will be talking about our work, smooth zero-knowledge hash functions, which is a joint work with Behzad Abdulmaliki and Helger Lipma. So let me begin with the notion of smooth projective hash functions, which is the main primitive in our work. So smooth projective hash function, or SPHF, is a cryptographic primitive consisting of some algorithms. There is a keygen that generates a key pair of HK and HP, where HK is a secret key and HP is a public key. And then there are two algorithms, hash and projective hash, that compute a hash value. So hash takes as input this secret key and some statement X and compute the hash. And projective hash takes as input the public key HP and the witness that should correspond to the statement X and output some hash value PH. And if W is the witness corresponding to the statement X, then the two hash values should be the same. That's the correctness property for SPHF. We have also a smoothness property, which says that if X is not in the language, meaning that there is no witness for this statement, so there is no way to compute the projective hash anymore, the hash value should be random. So more formally, a projective hash function consists of 5 algorithms. There is a setup algorithm that generates the language parameters and fix the language and NP language. And we have a hash keygen that takes as input this language parameter and output some secret HK. A projective keygen that takes as input the secret key, the language parameter, and sometimes the statement. So depending on the type of the SPHF we are considering, it may takes as input the statement or not. And finally, it outputs some public key HP. And then we have the hash algorithm that outputs some hash by using the public statement X and secret key HK. And projective hash that takes as input the public key HP and the statement and some witness W. And then if as I said before, the correctness says that for any pair of X and W in the relation, the two hash values should be the same. And if X is not in the language, then the pair of public key HP and this hash value computed by the hash algorithm should look indistinguishable from HP and some random value in the range of the hash function. So it basically says that the adversary, by seeing HP and this hash, doesn't learn anything about, cannot distinguish this hash from a random value. So SPHF have several applications, but the one we are considering mostly is the non-interactive zero-knowledge or zero-knowledge arguments. And what we want to do is to make this zero-knowledge proof, to construct subversion-resistant zero-knowledge proofs based on subversion type of a smooth projective hash function. So let me explain a bit about what is a zero-knowledge proof system in a trust model and what I mean by subversion. So a proof system in a trust model, we have 3 types of players: a trusted party that generate a reference string, a string called a CRS. And because this party is trusted, so both the prover in the left side and the verifier in the right side know that this CRS is generated honestly. And then they interact with together, and at the end, the prover in the left side tries to convince the verifier that the statement X, which is public, is inside the language, inside some NP language. And they use this CRS to check this. I mean, the prover used this CRS to convince the verifier, and verifier used the CRS to check the claim by the prover. And this is what we call a proof system. And then the zero knowledge property states that this flow of transcript between the prover and verifier, it should not reveal any information about the witness of the prover, W. And by subversion, what we mean is that subversion means that now, what if this trusted party is not trusted anymore? And what if this CRS is generated maliciously? So actually, the purpose of subversion zero knowledge is to make sure that what if we reduce the level of trust and see if we can change the model a bit and make the trust a bit less, such that at the end we still have some meaningful notion of zero knowledge and security. And so to see how SPHF that I described at the beginning is related to zero knowledge proof, so I have this slide which show how we can construct honest verified zero knowledge proofs from SPHFs. So the idea is that this CRS generator just generates some language parameter and define the CRS to be the language parameters. And now there is an interaction between the prover and verifier. The verifier generates the key pair of the hash and send the public key HP to the prover. And now the prover compute pH, the hash value pH, by using the witness and send pH to the verifier. And now verifier accept the proof if this pH is equal to the hash of a statement. So by the correctness property of the SPHF, we know that the two hash values are the same if the prover is computing the hash by using the valid witness. So, but the important point here is that it's not really zero knowledge, because we are assuming that the first message from the verifier is generated honestly. And in fact, there is no guarantee that if HP is maliciously generated, then there is no way to make sure that the zero knowledge property holds, or more formally, if we can simulate the hash computed by the prover. So, and that's the purpose of the main motivation for this notion of trapdoor SPHF. Trapdoor SPHF is a type of SPHF which is in the trust model. So now there is also a CRS, a reference S string, that has a trapdoor, and that trapdoor allows to compute the hash in a different way. So to be more formal, there are several algorithms that many of them are similar to smooth projective hash functions. But here in TSPHF, we also have a var HP algorithm that verifies if an HP is generated correctly or not. I mean, it checks if HP is well formed or well defined, and then it computes a hash by using the statement and the trapdoor of the CRS. And now in this case, the zero knowledge property states that this TH computed by the trapdoor should look indistinguishable from a PH that is computed by using the witness. And in this case, we can make sure that the hash value is not revealing any information about the witness. But now, even though this notion looks good for considering subversion, but it's not completely, I mean, here, even though we are removing the trust to the verifier, but we are still, we should rely on a trust to the CRS generator. But so if we consider this as a subversion problem, we are just shifting the problem from trusting to the HP generator, which is the verifier, to trust to the CRS generator. And that's why we define this notion of smooth zero knowledge hash functions. So the notion is very similar to trapdoor SPHF, but here we have two new algorithms. One is so setup hash keygen, projective keygen, and projective hash are the same as before, where HP is similar to the algorithm in trapdoor SPHF. But here we have also var pair, which is an algorithm that checks the well-formedness of the language parameter, and also a subhash, which is similar to the t-hash algorithm in trapdoor SPHF. But we go into the details of this subhash to see how we can simulate the hash value. The properties are similar to trapdoor SPHF, but here we have also subpair smoothness, meaning that a smoothness should hold even if the language parameter is created maliciously. And then the zero knowledge property states that even if HP and the language parameter are generated maliciously, then either we can detect this by these var HP and var pair algorithms, or we can simulate the projective hash. So when we define this notion of SZKHF, we first consider the zero knowledge property in the plain model, which basically it says that for any subverter Z that output HP, we compute hash 0 H0 or H1 either by a projective hash algorithm or by this subhash algorithm. And then assuming that the verification of HP, where HP passed the verification for HP, for public key HP, then the adversary should not be able to distinguish H0 from H1. But this is a very strong notion because we then show that it's not possible to have this type of zero knowledge property in the plain model if we just use black box techniques. And the reason, I mean, the impossibility is very similar to the impossibility we have for 2-round zero knowledge proofs, because here the simulator doesn't have any trapdoor to compute the proof, to compute the hash. So we have two alternatives for this. We either rely on some trust model, which is the RPK model, registered public key, which is weaker than the CRS model. And then we have also another construction in the plain model, which is based on non-black box assumptions. So I will mostly focus on the last one. I mean, for the construction in the plain model, which uses non-black box techniques. So in this case, we define the subversion. We define this notion of zero knowledge in the following way. We say that for any subverter Z, there exists an extractor that have a non-black box access to this subverter. So he has the code of the subverter, and by that he can output a function of the HK, kappa HK, and this kappa HK, which is the output of the extractor, is enough to be given to the subhash algorithm to compute a hash. So again, we compute H0, H1. H0 is computed by the projective hash, and H1 is computed by the subhash. And then we give one of these H0 or H1 to the adversary. And assuming that the pair of statement and witness is inside the language, and assuming that HP generated by the subverter passes the verification, then the adversary should not be able to distinguish these two hash values, one computed by a real, based on using a real witness for a statement X, the other is by using the output of the extractor, which is a function of the HK. And then we show that in the RPK model, we show that, which is something weaker than the CRS model, we show that the previous construction of TSPHF is also secure in this model. And in the plain model, we show that we give a construction of sub ZK SZKHF, a smooth zero knowledge hash function in the plain model, based on any SPHF that is constructed from a notion of a diverse vector space that I didn't explain here. It's just a basic framework for constructing SPHF. And finally, we show the security proof in the based on knowledge assumption. We show that subpair smoothness holds based on a new type of decisional Diffie-Hellman assumption, and zero knowledge property holds based on some knowledge assumption that we show in the paper that it holds also in the algebraic group model. So that was my talk, and if you're interested, also the full version is on ePrint, so you can check the full version also.
Thank you, Hamid Reza. Perfectly timed. Are there any questions?
Yes, any questions offline? No questions from this side. Would you?
Do you have any questions?
No,
Okay.
nothing
All
from
right.
my side. Any questions online? You can check.
Yeah. I don't seem to see any questions on the chat. So I'm assuming there are none. Hamid Reza, did I hear you right when you said that you assumed that your language was in NP? That X was taken from a language from NP?
Yes, so we are giving this construction for any arbitrary language, NP language,
Okay.
which means that there is a statement and also a witness.
Okay.
And by that witness, we compute a hash, or by using only the state.
So I have a sort of silly question, which is, what if you took an X which was from a language in co-NP? Does the same framework play out, or is it somewhat different?
Yeah, I think by NP, I mean just a general language that, I mean, a pair of a statement and witness is enough to define this SPHF for I mean, computing the hash in two different ways.
Okay. If there are no other questions, we'd like to thank the speaker again, and we're ready to move on to the third talk, which is another use of the 5-card trick, card minimal. Oh, good. That's the applause. Yeah. Another use of the 5-card trick, card minimal secure 3-input majority function evaluation. And Kodai Toyoda is going to give the talk. Over to you, Kodai.
Okay. Can you see my screen?
Yes, we can. Go ahead, please.
Okay. Hello, everyone. I'm Kodai Toyoda, a student of Tohoku University. Today, I'm going to talk about another use of the 5-card trick, card minimal secure 3-input majority function evaluation. This is the joint work with Daiki Miyahara and Takaaki Mizuki. Here is the outline of my talk. Let me start with introduction. First, I'd like to talk about secure multi-party computation. Let's consider the case where 3 players have private input bits A, B, and C, and they want to know only the value of a function f of A, B, C without revealing their input bit. The computation that makes this possible is called secure multi-party computation, MPC for short. Card-based cryptography is one of a convenient solution to perform MPC. In this study, we use a 2-card deck of cards consisting of black and red cards whose backs are all identical. Using 2 cards, we encode a Boolean value like this. Black to red represents 0, and red to black represents 1. Based on this encoding, a player can commit a private input to a pair of face-down cards, keeping its value hidden. We call it a commitment to the bit A. If A equals 0, then the left card is black, and if A equals 1, then the left card is red. Now let me introduce 5-card trick, which is the first card-based protocol proposed by Denbor. This protocol takes commitments to X, Y, and 1 additional red card as input, and output X and Y. Assume that there are commitments to X and a commitment to Y, as well as an additional red card like this. This 5-card sequence is the input to the protocol. Then swap the 2 cards of the commitment to Y to make a commitment to bar Y. That is, these 2 cards are a commitment to the negation of Y. In addition, turn over the leftmost red card. Please note that in this case, for each input, the sequence of cards is like this. That is, 3 red cards are cyclically consecutive, i.e. the first, second, and fifth cards are red, if and only if x and y equals 1. Then apply a random cut to the sequence of 5 cards. A random cut is a shuffling operation. Let me show a video of a random cut. This shuffle shifts the positions of the sequence without changing the order. And if a random cut is applied to a sequence of 5 cards, it transitions in these 5 cases, each with a probability of 1/5. These sequences are all identical up to rotation. Applying a random cut, we get the following state. Then reveal the 5 cards. If the 3 red cards are cyclically consecutive, we have x and y equals 1, and otherwise we have x and y equals 0. And let me explain our target. As you might see, 5-card trick is easy to understand, and it can be used for teaching lay people the concept of secure multiparty computation. But many lay people would consider that such a secure 2-input AND computation may be somewhat useless. Because once Alice having the private bit of x equals 1 knows the result of the computation, she gets to know Bob's bit. Of course, this is inherent, but it would be worthwhile to find more suitable functions for educational purpose. And in this work, we consider the 3-input majority function, majority of ABC, as a promising function defined like this. Now, I'd like to explain 3-input majority protocol in card-based cryptography. Given 3 commitments to bits A, B, and C, together with some additional cards, players apply a series of operations such as rearranging, shuffling, and turning over cards to get the output. And a protocol whose output is given with a commitment is called a committed format protocol, and a protocol whose output is not given with a commitment is called a non-committed format protocol. Now let me show the existing 3-input majority protocols. In 2013, Nishida et al. Presented the first 3-input majority protocol using 8 cards. And since then, several other majority protocols have been proposed. Please remember that the first protocol and the last protocol do not use private operations. And allowing private operations is a strong assumption that a player may manipulate the cards privately, say behind their back, while making sure that the other players do not see the movement. So we focus the protocols that do not rely on any private operations. There are 2 existing protocols without using private operations. Both protocols need 8 cards. That is, they use 2 additional cards like this, so it has been an open problem to reduce the number of required additional cards. Now let me present our contribution. We construct a 3-input majority protocol with 6 cards. This is the first card minimal 3-input majority protocol, and card minimality means to use no additional cards. Also, we show how to transform our non-committed format protocol to committed format 1. Due to time constraints, I will skip this part. Now let me present our card minimal 3-input majority protocol. We constructed a 3-input majority protocol with 6 cards. Let me explain the idea behind our majority protocol. We make use of the following simple facts on the 3-input majority function majority of A, B, C. If A equals 0, then majority of A, B, C equals B and C, and if A equals 1, then B or C. As we can compute B and C by using the 5-card trick, and we need to how to compute B or C. To solve this, we propose the 5 code or protocol by modifying the 5 code trick slightly. I'll explain these 4 variants of 5 code trick. The first one is let-based AND protocol. This is AND protocol with a let code as an additional code, and this protocol is exactly the same as the 5 code trick. The second one is let-based OR protocol. This is OR protocol with a let code as an additional code. And let us write commitments to X and commitments to Y using X0, X1, Y0, and Y1 like this. Then rearrange the 5 codes like this. In this case, 3 let codes are cyclically consecutive if and only if X or Y equals 1. So X or Y can be computed by applying a random cut. The third one is block-based AND protocol. This is AND protocol with a block code as an additional code. And first, rearrange the 5 codes like this. And in this case, 3 block codes are not cyclically consecutive if and only if X and Y equal 1. So X and Y can be computed by applying a random cut. The last one is block-based OR protocol. This is OR protocol with the block code as an additional code. First, rearrange the 5 codes like this. And in this case, 3 block codes are not cyclically consecutive if and only if X or Y equals 1. So X or Y can be computed by applying a random cut. These 4 protocols satisfy the following relationship. Let's consider the let-based AND as a start. If the second and fifth codes are swapped, the let-based OR is applied. And if the first code is replaced with a block code, the block-based OR is applied. And if both operations are performed, block-based AND is applied. We use the relationship between these 4 protocols to construct our majority protocol. First, place the commitments to A, B, and the negation of C. In the case of A equals 0, please recall that majority of A, B, C equals B and C, and if A equals 1, it is B or C. And let us apply a random cut to the second through 6 scores. Since the let-based AND will be applied if A equals 0 and the block-based OR will be applied if A equals 1, we can obtain the value of majority function. However, depending on whether the output is let-based or block-based, the value of A will be leaked. To resolve this issue, we randomize the state so that if A equals 0, either the let-based AND or the block-based AND is applied with equal probability, and if A equals 1, either the let-based or the block-based OR is applied with equal probability by applying the random bisection cut. A random bisection cut is shuffling operation that bisects a sequence of cards, swaps the 2 halves at random as like this. Therefore, the shuffle results in 2 possible cases, depending on whether the 2 halves are swapped or not, each with a probability of 1/2. After applying a random bisection cut, we have these 4 possibilities. Then if we apply random cut to the second through 6 cards, then either the let-based AND or block-based AND is applied when A equals 0 and with the equal probability. And either the let-based OR or block-based OR is applied when A equals 1. So the value of A cannot be leaked, while the value of majority function can be obtained. Thus, we can compute majority of A, B, C. Here is the description of our majority protocol. And step 1, first place a commitment to A, a commitment to B, and a commitment to the negation of C like this. Step 2, rearrange the codes like this. Step 3, apply a random bisection cut to the leftmost 4 cards. After applying the random bisection cut, the sequence of cards will be one of these 2 ways with a probability of 1/2 for each. And step 4, rearrange the codes like this. Now, if a random cut is applied to the second through 6 cards, one of these 4 protocols will be applied. And step 5, apply random cut to the second through 6 cards. And step 6, reveal all cards to obtain the output. And first, reveal the first card, and next, reveal all the remaining 5 cards, and then the sequence of cards will be one of these. In the case of false cards is red, if the 3 black cards are cyclically consecutive, we have majority of ABC equals 0. Otherwise, we have majority of ABC equals 1. In the case of the false card is black, if the 3 red cards are cyclically consecutive, we have majority of ABC equals 1, and otherwise we have majority of ABC equals 0. This is our majority protocol. As you can see, the number of shuffles in this protocol is 2. Next, I'll give a description of our majority protocol in a formal way based on the computation model of card-based cryptography. In card-based cryptography, there are 3 main operations performed on a sequence of cards, namely permuting, turning, and shuffling. Let us assume a sequence of n cards. These operations are denoted like this. And pi is a permutation applied to the sequence of cards. And the large T is a set of indexes indicating that T's cards is turning over for every T. And the large pi is a permutation set, and the large F is a probability distribution on large pi, indicating that pi is drawn according to large F and is applied to the sequence of cards. And note that nobody knows which permutation in large pi was applied. If the probability distribution large F is uniform, we may omit it. And here is a pseudocode for our majority protocol. As you can see, this protocol is very simple. And next, let me move on to correctness and security. We make use of the KWH3 to verify the correctness and security of our proposed protocol. KWH3 makes it possible to visualize the state transition of the cards like this. And if one can write the KWH3 satisfying some properties for a protocol, then it automatically implies that the protocol is correct and secure. We can write the KWH3 of this protocol satisfying the required properties like this. Thus, our protocol is correct and secure. Finally, I conclude this presentation. In this work, we constructed the first card minimal linked majority protocol using only 6 cards. And that's all. Thank you for listening.
Thank you very much, Toyoda-san. Are there any questions?
Yeah, so any questions offline? Not from the audience. I have a couple of questions. So first of all, there is a comparison table that you showed probably in slide number 21. So my question is that you said that the runtime of those algorithms, the existing algorithms and yours as well, is finite. So can you quantify that number a bit? What do you mean by finite here?
Sorry, could you repeat your question?
Yeah, so when you say runtime is finite, what do you mean by finite here?
Yes, finite means this protocol finished a fixed number of operations.
So is it like that for all the all these 5 protocols?
Yes. I skipped this protocol, our Las Vegas protocol, but there is Las Vegas runtime protocol. This means it has a loop in the protocol, so it doesn't terminate within a fixed number of operations.
Yeah, perhaps you should use the word definite or bounded. And I guess in the other one, you're saying that it's not definite, but it terminates with some kind of distribution given by Las Vegas, right? Some kind of random distribution, random number which follows a distribution. Is that what you mean?
Yeah. Sorry, could you repeat?
Yeah, I think when you say finite, you probably want to say definite or bounded.
Yes.
Okay. Are there any further questions?
Yeah, my next question is actually related to your slide number 53. So, is it possible to share the share your screen again?
Yes. 53.
53. 53.
Okay.
Yeah. So in this case, in step 2, when you rearrange the cards, so the first card
Yes.
always remains to be the same, right?
Yes.
So, I mean, just out of curiosity, it's probably a very primitive question. So, is it possible that this scheme will lead to a partial information leakage?
Sorry, I can follow you. So could you repeat your question?
Yeah. Okay. So my question is that since the first card is not rearranged, it kind of is the same. So, is it possible that this scheme will result in an output which is, which will lead to partial information leakage?
Yes. So because step 3, we apply a random bisection cut. So first card is swapped to 3 third cards in probability 1/2. So information cannot be leaked.
All right. Thank you. That's all from my side. Over to you, Professor Prasad.
Yeah. Are there any further questions? Well, this was a fascinating talk, and thank you very much. I think we've a few minutes ahead of schedule, but we've come to the end of the session. And I'd like to thank the speakers again. And I'd like to remind the audience and the speakers that there are breakout Google Meet venues where you can interact with the 3 presenters and ask them further questions. And once again, thank you all. Thank you very much for attending, and thank you to the speakers. That was a wonderful session. Thank you very much.
This is a time for a short break of 15 minutes. We'll be right back to the next session at 6:30 p.m. IST sharp. Thank you.